Range and standard deviation. In the preceding section, we introduced three types of average values for data set: the mean, the median, and the mode. Some characteristics of a set of data may not be evident from an examination of averages. For instance, let us consider this table. This is a table of the soft drink dispensing machine that should dispense an 8 ounce of your selection into a cup. This table shows data for two of these machines. The mean data value for each machine is 8 ohms. However, look at the variation in the data values for machine 1. The quantity of soda dispensed is very inconsistent. In some cases, the soda overflows the cup, and in other cases, too little soda is dispensed. The machine obviously needs adjustment. Machine 2, on the other hand, is working just fine. The quantity dispensed is very consistent with little variation. This example shows that average values do not reflect the spread of dispersion of data. To measure the spread of dispersion of data, we must introduce statistical values known as range and the standard deviation. The range of a set of data is the difference between the greatest data value and the least data value. For instance, find the range of number of ounces dispensed by machine 1 as shown before. So we could see that the greatest number of ounces dispensed in machine 1 is 10.07 and the least is 5.85. The range of the number of ounces dispensed is 10.07 minus 5.85, which is 4.22 ohms. Let's try finding the range of the numbers of ounces dispensed by machine 2. The greatest value of ohms dispensed by machine 2 is 8.03, while the least is 7.95. To get the range, we divide the maximum value with the minimum value. Hence, 8.03 minus 7.95 is 0.08. Now, let us consider this table. The range of a set of data is easy to compute, but it can also be deceiving. The range is a measure that depends only on two most extreme values, and such is very sensitive. A measure of dispersion that is less sensitive to extreme values is the standard deviation. The standard deviation of a set of numerical data makes use of the amount by which each individual data value deviates from the mean. This deviation represents by x minus x bar are positive when the data value x is greater than the mean x bar and are negative when x is less than the mean x bar. The sum of all deviation, x minus x bar, is 0 for all sets of data. This is shown in this table for machine 2 data. Because the sum of all deviations of the data values from the mean is always 0, we cannot use the sum of the deviation as a measure of dispersion for the set of data. Instead, the standard deviation uses the sum of the squares of the deviation. If x1, x2, x3 up to xn is a population of n numbers with a mean of u, then the standard deviation of the population is standard deviation is equal to the summation of the quantity x minus mu squared over n. However, if x1, x2, x3 up to xn is a sample of n numbers with a mean of x bar, then the standard deviation of the population is standard deviation equal to the square root of the summation of x minus x bar squared over n minus 1. The most statistical application involved a sample rather than a population, which is the complete set of data values. Sample standard deviation are designated by the lowercase letter s. In those cases in which we do work with the population, we designate the standard deviation of the population by the small letter sigma, which is the small letter sigma. We can use the following procedure to calculate the standard deviation of n numbers. Procedure for computing standard deviation. First, determine the mean of the n numbers. Second, For each number, calculate the deviation or the difference between the number and the mean of the number. Third, calculate the square of each deviation and find the sum of these squared deviations. Fourth, find the data of the population. Then divide the sum by n. If the data is a sample, divide it by n minus 1. And lastly, find the square root of the quotient in step number 4. For instance, find the standard deviation of this sample: 2, 4, 7, 12, 15. Step 1. Find the mean of the number. Thus, the mean of the number is x bar is equal to 2 plus 4 plus 7 plus 12 plus 15 over 5, which is equal to 40 over 5, which is 8. Step 2. For each number, calculate the deviation between the number and the mean. Thus, we see in this table the summary of the said step. Step 3. Calculate the squares of each deviation in step 2 and find the sum of this squared deviation. Notice that the sum of the squared deviation is 118. Step 4. Now, because we have a sample of n equal to 5 values, divide the number 118 by n minus 1, which is 4. And we get 118 over 4, which is equal to 29.5. The standard deviation of the sample is s equal to the square root of 29.5, which is 5.43. Let's consider this data. A consumer group has tested a sample size of 8 size D batteries for each of 3 companies. The result of the test are shown in the following table. According to these tests, which company produces batteries for which the value representing hours of constant use have the smallest standard deviation? Thus, the solution is, we find that the mean of each sample of batteries is equal to 7 hours. However, the batteries from Ever So Bright have the standard deviation of 1.328 hours. The batteries from Dependable have a standard deviation of 0.719 hours, while the batteries from Beacon have a standard deviation of 0.877 hours. The battery from Dependable have the smallest standard deviation according to these results. The Dependable company produces the most consistent batteries with regard to life expectancy under constant use.